Okay, let us finish off this chapter by looking at the construction of R from uh, our rationals. Okay, so this process is called uh, construct constructing the real field, uh, the real field, and the method is called Dedekind cuts. Dedekind cuts. Dedekind used this construction to formalize the definition of rationals. Now, this might seem slightly unintuitive and artificial rather than coming up naturally, and um, it is slightly like that. I mean, the concept of reals far predates Dedekind. Like, people knew the existence of non-rational numbers, right? People knew back even from the days of Pythagoras that there are numbers which are not rationals. But how to formally write these numbers, how to formalize this concept was a big problem. And so Dedekind um, used this method to formally write down what real numbers are. So it's slightly unintuitive, but it's a good exercise in how to do it. Okay, so the members of R, members of a field R that we don't know yet, will be certain subsets of Q, will be certain subsets of Q rationals called cuts, called cuts. And what is a cut? A cut is defined by definition is any set alpha which is a subset of Q with the following three properties. With following three properties. Now, I am not going to go into full details regarding this. I will cover the important proofs, but I will leave some of these things for you. So what are the three important properties? Well, alpha is not empty. Alpha is not empty, and alpha is not equal to Q. Okay, so it has to be a proper subset of Q. Second, if P belongs to alpha and Q belongs to the reals and Q is actually smaller than P, then Q belongs to alpha. Okay, so now with the preface that you know what intervals are in real numbers and everything, you're looking more or less as at an interval from negative infinity to whatever the number alpha is going to be. Okay, that is what is going to be a cut. But if you don't have negative infinity as a number and you don't know what real numbers are, you can't define the interval, right? So this is what it is defined as. And third, if P belongs to alpha, then P smaller than R for some R belonging R in alpha. Okay, so more or less everything is an open interval. You're looking at open intervals, not closed intervals. Okay, in terms of uh, the mental picture. Okay, so we will denote, we'll use P Q R dot 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 for rationals. and alpha, beta, gamma, dot, dot, dot for cuts. Okay. Now, part 3 basically says that there is no largest element in the set. Okay. So basically, in terms of drawing the thinking of as an interval, it's an open interval at if I call the cut as alpha, then at alpha. Okay. Point 2 basically says if P belongs to alpha and Q does not belong to alpha, then Q has to be greater than alpha. Okay. So again, the mental picture you should be having is an open interval from negative infinity to a point alpha. Okay. We don't know if alpha is real or rational. You can use it for both, but that's the mental picture you should be having. Define alpha smaller than beta to mean alpha is a proper subset of beta. Alpha is a proper subset of beta. Okay. Since alpha and beta are sets, I'm going to say, well, they're not really numbers, right? But I'm going to define alpha smaller than beta to mean alpha is a proper subset of beta. So it is clear that alpha smaller than beta and beta is smaller than gamma implies alpha smaller than gamma, since transitivity is a property of sets, set inclusions. Okay. And it is also clear at most one of the following holds. So you can't have all three of these. At most one of them holds. We can't yet show. We have to argue that exactly one of them holds, but it is important to note at most one of them holds. Two of them can't hold. Okay, so to show that at least one of them holds, to show at least one holds, assume the first two don't hold. First two don't hold. Okay, if the first two don't hold, then alpha is not a subset of beta. Then alpha is not a subset of beta, right? Which means therefore, there exists some P belonging to alpha such that P does not belong to beta, right? That's literally what it means. Since that is literally the definition of alpha not being a subset of beta. Okay, now if Q belongs to beta and Q is greater than P, then P belongs to beta. Then P belongs to beta by property 3. By property 2. Right? Was it property 2? Right. Yeah, by property 2. Therefore, it follows that P has therefore Q has to be smaller than beta. Q has to be smaller than P. Q smaller than P, and therefore, and Q belongs to alpha by property 2. Again, property 2 says, well, P is an alpha, Q is smaller than P, then Q is an alpha. Well, therefore, every element of beta is an element of alpha. So, beta is a subset of alpha. Great. Now, as beta is not equal to alpha, we conclude beta is a proper subset of alpha, implying beta is smaller than alpha. Okay, and so at least one of these properties is true, at most one of these properties is true, so exactly one of these properties is true. Okay, so it's a strict order. Step 3. The ordered set R has the least upper bound property. The ordered set R has the least upper bound property. The least upper bound property. Okay, this is something that clearly is not true in rationals. This is something that is going to say, oh, now what I am looking at, the set I'm looking at, it contains rationals somehow, we'll show that, and it is actually bigger than rationals. It is a more powerful set. It has the least upper bound property. Okay, so to prove this, let A be a non-empty subset of R. Let A be a non-empty subset of R. Keep in mind the elements of R are cuts. Okay, so A as a non-empty subset of R is a collection of cuts. Okay, and assume beta belonging to R is an upper bound of A. Is an upper bound of A. Then we want to show A has some least upper bound, right? Here's how we do it. Define gamma to be the union of all alpha in A. Okay, what does that mean? i.e. P belongs to gamma, if and only if P belongs to alpha for some alpha belonging to A. I am clarifying it here. I'm slowly soon going to be assuming that you understand what union and intersection mean. If you're not familiar, I'm using it, expanding out for some things, but slowly I'm not going to be expanding. I'm going to say let alpha be in the union, whatever, that's it. Okay, now then we want to show gamma belongs to R and that gamma is equal to supremum A. So what does it mean by gamma being in R? We want to show that gamma is actually a cut. Okay. So how do we show that gamma is a cut? We have to show the 3 properties for gamma. Okay. So first, since A is not empty, since A is non-empty. There exists some alpha not belonging to A. Okay, by property 1, this alpha naught is not empty. This alpha naught is not empty, is non-empty. So there is some P where, so there is some P which is, well, there is an easier way to say this. This is not empty. Well, since alpha naught is a subset of gamma, gamma is not empty. Why is it a subset of gamma? Gamma is a union of everything. Okay. That does not complete property 1, however, because we also need to show it's not, what do you call it? Not Q. So next, since gamma is a subset of beta, as alpha is subset smaller than beta for every beta, as since alpha subset of beta for every alpha in A, and beta is not equal to Q, gamma is not equal, and beta is a proper subset of Q, right? As a cut, it is not equal to Q, it is a subset of Q, right? Therefore, gamma is not equal to Q. Therefore, property 1 holds. Okay. Did I call them 1, 2, 3 in some other kind of letter? Because that would be confusing. Yes. So let me refer to them by these letters. The book uses these letters. I am going to be super lazy later. So property 1 holds. Okay. To prove property 2 and property 3, so, and do I need to, okay, let me just raise this. To prove property 2 and property 3, pick gamma, pick P belonging to gamma. P belonging to gamma. Since it's not empty, blah, 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 there is some P such a thing holds. Then, by definition of gamma, P belongs to some alpha 1, right? For some alpha 1 belongs to A, right? And if Q is smaller than P, then Q belongs to alpha 1, right? By property 2. Therefore, Q belongs to gamma, proving 2. Okay? Now, if R belongs to alpha 1 and R is greater than P, then R belongs to gamma, right? And therefore, gamma satisfies property 3. Satisfies 3. Okay, so all 3 properties hold. And hence, therefore, gamma is an R. Okay. Great, we have shown that gamma is an R, but that does not complete the proof of whatever step I'm trying to prove. Because I'm trying to show least upper bound property, we showed gamma is in R, we want to show gamma is the supremum of A. Well, clearly, alpha is smaller than or equal to gamma for every alpha in A, right? So it is an upper bound, therefore it is an upper bound, therefore upper bound, right? Now suppose there was some delta smaller than gamma, right? Then there exists some S which belongs to gamma such that S does not belong to delta, right? Well, but what is the definition of S? What is the definition of gamma? Therefore, there exists some alpha belonging to A such that S belongs to alpha, right? Therefore, well, S belongs to alpha, S does not belong, and S does not belong to delta. Therefore, by properties of cuts before, we know that delta is smaller than alpha, and therefore, and hence, delta is not an upper bound, not an upper bound of A, which means alpha is the least upper, gamma is the least upper bound possible. Therefore, gamma is the least upper bound of A, i.e. gamma is equal to supremum of A. Okay? And that proves that my set R has the least upper bound property. Great, we have the defining condition of what we will call the real numbers. Step 4. If alpha is in R and beta is in R, then define alpha plus beta by definition is the set R plus S such that R belongs to alpha, S belongs to beta, and we are taking the set of R plus S, right? Alpha and beta are subsets of rationals. We can add elements of rationals. Alpha plus beta is going to be defined as such an element, okay? We want to show that this addition actually makes sense and the axioms hold, okay? Define 0 star to be the set of all all negative rational numbers. It's equal to set of all negative rationals. Okay? Then it is clear that it is a cut. Okay, so all three properties of a cut are easily satisfied. Now we want to hold a show that the axioms need to show, or want to show axioms of addition hold for this definition of R. Hold for R with 0 star playing the role of 0. Playing the role of 0. Okay? I am not going to be showing all of them. Okay? I will just show A1 and A5. You can look at the book Appendix 1. I think it's just after the chapter, and it proves all of these. but I'm just going to show A2, A3, A4 left as exercise. Therefore, U to complete will show, we will show A1, A5. Okay, so let's try to do A1 first. We have to show that A alpha plus beta is a cut. I have to show alpha plus beta is a cut. The idea is A2, A3, A4 more or less follow exactly the same way as A1. Okay. First of all, property one is more or less clear. Clearly, alpha plus beta is not empty. Is not empty. Right? Because there is an element in alpha, there is an element in beta. Take their sum. That is not empty. Right? Then take R prime not in alpha, S prime not in beta, then R prime plus S prime is greater than R plus S for every R in alpha, S in beta, right? Therefore, R prime plus S prime does not belong to alpha plus beta. Oops. Alpha plus beta. Which means, therefore, alpha plus beta is a proper subset of Q, right? And therefore satisfies 1. Therefore satisfies property 1. Great. For property 2 and 3, pick P in alpha plus beta, right? What does that mean? If P is an alpha plus beta, then there exists R comma S, R comma S in, R in alpha, S in beta, such that P is equal to R plus S. Okay. If Q is smaller than P, then Q minus S is smaller than R, right? Because P minus S is just R. So Q minus S belongs to alpha, right? Therefore, Q, which is equal to Q minus S plus S, belongs to alpha plus beta, right? Therefore, 2 holds. 2 holds. Okay. Now choose T belonging to alpha such that T is greater than R. Then actually P is smaller than T plus S, and T plus S and T plus S is contained in alpha plus beta. And so I have a bigger element in alpha plus beta, therefore 3 holds. Okay, and that shows A1. Therefore, A1 holds. A1 holds. So we have shown property A1. For A5, we need to show something slightly more non-trivial, right? So fix alpha belonging to R. Let beta be the set of all P, be the set of all P, set of all P with the following property, with the property there exists R greater than 0 such that minus P minus R does not belong to alpha. Okay? What does that mean? It means some rational number smaller than negative P is not in alpha. Okay? Because negative P is a rational number, you're subtracting some rational number R, and together it is smaller than alpha. Okay? Want to show that R beta belongs to R, and alpha plus beta is equal to 0 star. And then, by definition, beta would be more or less fulfilling the role of negative alpha, which is what we want to show in property 5, that the additive inverse exists, right? So, which is why we need to define a smart cut, more or less. So, if S does not belong to alpha, and P is equal to negative S minus 1, then minus P minus 1 does not belong to alpha. Okay? And hence, P belongs to beta. Okay? Why does this hold? If S does not belong to alpha, then minus S minus 1, if you define P as minus S minus 1, then minus P is going to be S plus 1, right? And minus P minus 1 is just then S plus 1 minus 1, which is just S, right? And that is how we defined our beta to be. Minus P minus R. R is 1, so P belongs to beta. Great. So, therefore, beta is not empty. Beta is not empty. Okay. Now, if Q does not be, if Q belongs to alpha, then Q does not belong to beta. Okay. So so beta is not equal to Q. Beta is not equal to Q. Therefore, 1. Okay. Holds for beta. Why is that? Oh, sorry. This should be negative Q. If Q belongs to alpha, then why does negative Q not belong to beta? Well, if negative Q belong to beta, then negative Q minus R should not belong to negative Q minus R should not belong to alpha. Negative Q is just Q. If Q belongs to alpha, everything smaller than Q belongs to alpha. So it's pretty easy to check. It's direct computation. To show that it's a cut, we need to show properties 2 and 3. So pick P belonging to beta, and R greater than 0, and R greater than 0, such that, well, by defining property, minus P minus R is not in alpha. is not in alpha. Okay, if q is smaller than p, then, well, minus q minus r is actually greater than minus p minus r, right? Well, therefore, minus q minus r does not belong to alpha. If it belonged to alpha, minus p minus r, which is smaller than it has to belong to alpha. Therefore, q belongs to beta. And therefore, 2 holds. Show property 3, put t is equal to, let's say, p plus r over 2. Okay. Then clearly t is greater than p, since r we have taken to be positive, and minus t minus r over 2, which is equal to, and let me just write it on the next line, and minus t minus r over 2, which is equal to minus p minus r over 2 minus r over 2, is actually equal to minus p minus r does not belong to alpha. So I have found a bigger element, therefore t belongs to beta. So I found a bigger element which satisfies, which is in beta, therefore 3 holds, and therefore beta is a cut. This does not, however, prove, therefore beta belongs to R. The entire thing, we still need to show alpha plus beta is equal to 0, right? So if R is in alpha, and S is in beta, then clearly, well, negative S is not in alpha, okay? And therefore, R is smaller than negative S, which implies, therefore, R plus S is smaller than 0, and therefore, by definition, since this is true for every R and every S in alpha and beta respectively, alpha plus beta is actually a subset of 0 star. We want to show it is an equality. We have shown one way inclusion, we want to show the other way. So to show other way, pick V belonging to O star, pick new, because it matters. Pick new belonging to, actually, which way do I want? No, let's take, we have taken R as, so I want rational, so take V belonging to O star, put W is equal to minus V over 2. Okay? Then, well, if V belongs to O star, O star is a set of all negative numbers. V over 2 is negative, so minus V over 2 is then positive. So W is greater than 0. And therefore, by Archimedean property of rationals, by Archimedean property of rationals, I'm not going to write that, there exists and greater than 0, and there exists an n in naturals such that NW is in alpha, but n plus 1 W is not in alpha. Okay? Do I wanted this to be rational or integer? Actually, this is slightly wrong. This should be alpha and integers, not rationals. if my alpha was actually thinking about if alpha is more or less a negative real, n could be negative. But still, this Archimedean property implies this. Okay, so let p is equal to, in that case, negative of n plus 2w. Okay, then p belongs to beta, since p minus w does not belong to alpha, since negative p minus w does not belong to alpha, and v, which is by definition n w plus w plus p, right? Because it's, if you solve for it, it's just v is equal to negative 2w belongs to alpha plus beta, right? Well, so every element of 0 belongs to alpha plus beta, therefore 0 is a subset of alpha plus beta, therefore by the two parts combined, therefore alpha plus beta is equal to 0 star. Okay, and right beta is equal to negative alpha. Okay, step 5. Having proved the addition satisfies these properties, we want to show the propositions of addition and everything. We can show proposition 1.14 in the book holds, is valid in reals. So in my notes, I might not have referred to it as 1.14. So let's go back to see what exactly 1.14 was, which is slightly annoying. But this is a proposition about addition. So, i.e., actually, since you can, please look up the one in book. From next time onwards, maybe I should stick to the naming convention of the book, since we do use it at times. Okay, but proposition 1.14 is valid for R, and therefore we can show and we can prove if alpha plus alpha beta gamma belong to R, then and beta is smaller than gamma, then alpha plus beta is smaller than alpha plus gamma. Okay, so it is extremely easy to follow these, and I'm not going to be proving it. Basically follows from the definition of the cut, that any element of beta is also a subset of gamma, so every element of alpha plus beta is also an element of alpha plus gamma, that is a subset, right? So it is pretty easy to show. Now we want to show that multiplicative axioms hold. Axioms of multiplication. Hold. Multiplication. Hold. Okay. Things are slightly more annoying. Okay. Here, because product of negative numbers are product of negative rationals are positive, right? So if you take alpha times beta, if you take something that is super negative here and super negative there, then things could go wrong. Okay. However, product of two negative rationals being positive um, is troubled. Um, creates makes it slightly more annoying, makes it more cumbersome. Okay, and so to deal with this, we first restrict it to only a set of all reals, positive reals. So we restrict ourselves to R plus, which is all alpha greater than 0 star. Okay, so first we say that, okay, we are only going to define multiplication for positives, then we'll deal with it. So if alpha belongs to R, if alpha belongs to R plus and beta belongs to R plus, then define alpha times beta to be the set of all P such that P belonging to Q such that P is smaller than RS for some R belonging to R belonging to alpha, S belonging to beta, and for a very important note, R greater than 0, S greater than 0. Why do such R and S exist? Because alpha and beta are both positive reals. Okay? Define 1 star is equal to all Q belonging to Q such that Q is strictly smaller than 1. Okay? Then we show axioms of multiplication, and distribution hold in with R plus instead of R in place of F. Hold for R plus maybe. Hold for R plus. For R plus with 1 star in the role of 1. In the role of 1. Okay. The proofs are going to be exactly similar to proofs in step 4. So we are again going to omit it. Okay. Keep in mind alpha greater than 0, beta greater than 0 implies that beta greater than 0. Step 7. Step 7. Uh, Now we need to define what negative means. Okay. Complete the definition. Complete the definition of multiplication. Multiplication by setting alpha times 0 star is equal to 0 star times alpha is equal to 0 star, and that alpha beta is equal to one of these three things, minus alpha times minus beta if alpha is smaller than 0 star, beta is smaller than 0 star, minus alpha times beta if alpha smaller than 0 star, beta greater than 0 star, or okay, great. Oh, why didn't that work? Or the third one, a minus of alpha times negative beta if alpha is greater than 0 star and beta is smaller than 0 star. So what are we doing? Why are we defining this way? Well, it is easier to define. We have defined multiplication for negative numbers, positive numbers. But when we are looking at things as infinite intervals, more or less, there are going to be very big negative numbers which multiply to something really big positive, right? And that could complicate things. We don't want that complication. So we only look at positive things and then adjust for multiplication. Okay? These products that we are now dealing with are all defined in step 6 because they are positive. Okay? Now, everything multiplication, since this is all positive other than the negative, the outside negative, other than outside negative, other than the outside negative sign, the axioms of multiplication hold by 6. Axioms of multiplication hold by 6. Hold by step 6. Okay? And so the proof of distribution property, we break down into cases. The proof of distribution property can be broken down into cases, which the distribution property says alpha times beta plus gamma is equal to alpha beta plus alpha gamma. Breaks into cases. Okay. Example. You'll have to individually do it for all the cases. We're not going to do for all the cases. We're just going to show for one case. Suppose alpha greater than 0 star, beta smaller than 0 star, and beta plus gamma is greater than 0 star. So technically this means that beta is greater than 0 star, but I'm saying something stronger. Beta plus gamma is greater than 0 star. Then gamma is equal to beta plus gamma plus minus beta, right? Therefore, alpha gamma is equal to alpha beta plus gamma plus alpha minus beta as distributive law, distributive property holds in R plus, right? We already know that it holds in R plus. However, but alpha times minus beta is actually just minus of alpha beta, right? Therefore, rearranging alpha gamma plus alpha beta is equal to alpha beta plus gamma. Similarly for other cases. Okay, and so we prove that R is a real field, and in fact we have shown R is an ordered field with least upper bound property. R is an ordered field with least upper bound property. Great. However, the struggle does not technically end there. First of all, we have to show that Q is a subfield of this. So property 8, step 8. Step 8. For every R belonging to Q, let R star is equal to the set of P belonging to R, P belonging to Q, such that P is strictly smaller than R. Okay, then it is clear that R star is a cut. Clear that R star is a cut and R star belongs to R. Okay, these cuts satisfy the properties. They satisfy first, or let's say A, R star plus S star is equal to R plus S star. B, R star multiplied by S star is equal to R times S star. And C, R star is smaller than S star if and only if, so if and only if R is smaller than S. All these proofs are extremely easy because they just follow exactly from the definitions of a cut. Okay, so we are not going to exactly show these. And so this brings us to step 9. the most important step related to step 8, which is to show that we can find we can identify Q with Q star, which allows us to regard Q as a subfield of R. So we identified R by rational. We identified R belonging to Q with R star belonging to R, and showed R star preserves addition, multiplication, addition product, so addition, multiplication, and order of Q. Multiplication and order of Q. Okay. We can say that these elements Q star, they are not exactly the elements of R, but we can say it is this identification. It is this identification of Q with Q star, which is all elements R star, which allows us to regard Q as a subfield of R, Okay, so what we are not showing is that any two fields with least upper bound property are isomorphic. So that is to say, that will show that, oh, this R is unique. Okay. We are not showing. Note, we are not proving that any two fields, any two ordered fields with the least upper bound property, are isomorphic. I.e., R is unique. However, that is something that is true. Okay, so while we are not proving that, this is something that is true, and hence it completely characterizes R. This now completely characterizes R. Okay, and this is how you construct R as a ordered field which contains your rationals, and this is also the end of chapter 1. Okay, so I'll stop this video here.